Alright, in this video we'll be looking at some continuous probability distributions as opposed to the discrete ones we've been looking at in this series. So to get our head around this, I want you to imagine a cable stretched across two telegraph poles like this, and there's a bird who's going to fly onto it and land on some random point on the cable. And given we want to think of this like a random variable, you can imagine the bird sort of doing this over and over again and landing on some random point each time, okay? And we're going to be a little imprecise here for now, but the bird could land sort of anywhere with equal chance. Again, we're talking super loosely here. Then we can answer some simple questions just by gut feeling, like if we split the wire right down the middle and ask what's the chance the bird lands on the left. You'd of course say it's 1/2. If you split that section right down the middle again and then ask for the probability of landing only in that section, it would naturally be 1/4. And so you'd realize that the probability seems to be directly related to the length of the section you're looking at in comparison to the whole lot, which makes sense. All right. But you could ask, what's the chance the bird lands right in the middle there? Well, going off the intuition that probability has to do with length, then the length of a single point is 0, right? And so it only makes sense to assign a probability of 0 to that event. Okay, so this is why this situation needs to be handled with a lot of care. Okay, while some things should be almost obvious by common sense, other things perhaps break our intuitions, one of which is this very important fact that a probability of 0 no longer means something is impossible. It doesn't mean that anymore. Okay, the bird could well and truly land in the middle. That's an option. But based on our understanding of other simple cases we've talked about already, we're forced to say that it lands there with a probability of 0. Okay, and I know this might seem really weird if you haven't seen this sort of thing before, so I might give an additional example of this which might use a more familiar and numerical situation, but I'll put that in another video, so I'll put a link in the description here. But in any case, for now, rather than say that landing in the middle is impossible, we say it is almost impossible, and the big takeaway is for any probability distribution like this, the chance of landing exactly on any given value is always 0. Okay, that's the first weird thing. Okay, but how do we make precise sense then of what's going on here? See, what I might do is illustrate this situation of the bird sort of landing anywhere at complete random, is to visualize it by drawing a graph of just a horizontal line, that yellow one, like this. Now, this line does not directly mean probability. And right now, I don't think I've given it any meaning yet, but it seems like it'd be appropriate, it seems it'd be fitting to use a flat horizontal line to illustrate the fact that the bird is equally likely, sort of, to land on any part of the cable. Okay, so let's change things up a bit now. Let's sort of take this bottle here and spray half the cable with, bird attraction goo. This pink stuff here, and the bird loves it. Okay, so that's going to make the bird, let's say, twice as likely to land on the left half rather than the right half of the wire. Okay, so if we repeatedly release the bird, it might look a bit like this. It prefers the left side sort of twice as much as the right side. Okay, and we'll still insist that probabilities must add up to 1, and so if the left side is twice as likely as the right side, with a bit of thought, you might realize that the probability of it landing in the pink section must be 2/3. Okay, and the chance it lands in the non-goo section, the right side, must be 1/3. Okay, that's the only pair of numbers that satisfies those conditions, that the left is twice as likely as the right, and that in total they add up to 1. Okay, it's 2/3 and 1/3. They add up to 1, and 2/3 is double 1/3. Okay, now, how should the yellow line change then? Well, naturally, it'd do something like this. Okay, the left half has a higher chance, and the right half has a lower chance. Now, we still haven't assigned any precise meaning to the yellow graph, we're just playing around, okay, but it would make sense, I think, and I hope it makes sense to you as well, to illustrate it like that, okay? And we could do similar things with this situation. We could chop the right half into 2 again and say, well, what's the chance the bird lands in here? And we should still be able to answer, since the whole right section is 1/3, it should just be half of that, which gives us 1/6. Okay, and I think this is what's going to give us a huge clue as to how to move forward. Okay, for both making sense of the yellow graph and making everything we've done precise. Okay, see, we're looking for a measure of probability. One that takes both the height of the yellow graph we've been drawing and the length of the wire into account. Okay, so what sort of measure does that? Well, hopefully you can see the most sensible way to measure something by considering both of those things is by looking at the area spanned by those 2 dimensions. So looking at the area under the yellow graph covered by the section of the cable we're considering. Okay, so we can better illustrate this, I think, by changing the yellow graph to maybe something more complicated, I think, even like a curve like this. Okay, so we might expect that with this distribution, if we repeatedly let the bird land on the cable, we'd get something like this. It prefers the areas of the cable that have a higher yellow graph, okay? And so right now, the bird should favor the middle since the graph is higher there, but doesn't like landing on the edge as much since the graph is lower there. Okay, but again, I need to stop again and say be careful with this. The graph again does not tell you the probability of the bird landing on any particular point. Again, as discussed, the probability of landing on any particular point is always 0. Okay, and that is consistent with the fact that the area under the graph spanned by a single point is indeed 0. Okay, rather, in these sorts of distributions, right, the simplest meaningful events to consider are not points on the cable, but sections of the cable, intervals on the cable, if you will. Okay, then the meaning we give to the yellow graph is this. The probability of the bird landing in that interval of the cable is exactly equal to the area under the graph swept out by that section. Okay, so let's summarize, and hopefully the result of this next screen is something you can write down if taking notes is your thing. Suppose a random variable x follows what we call a continuous probability distribution. Okay, we might say x itself is a continuous random variable. Okay, what does this even mean? What sort of situations are we looking at here? It means a set of possible values is unlistable, in the sense that it is so enormous. The set of possible outcomes of this random variable is so huge that even an infinitely long list is not enough to hold them. Okay, see the end of the first video in this whole series, you need a reminder of what that's all about. Okay, now typically what that means for us in our course is that we're pretty much considering either the entire number line or some sort of interval on the number line. Okay, that's very different to all the other probability distributions we've seen before, okay, where the set of allowed values is a list of numbers or a list of options. Okay, so in this case, right, the set of possibilities is a whole interval, a continuous interval on the number line, or the entire number line, or maybe a bunch of intervals put together, something like that. Okay, so as a typical sort of real example, let's say we take like a measuring tape and we use it to measure the height of people all around the world, right? You could have babies with a small height, okay, or obviously people who are taller, okay, and actually the largest recorded height we have, according to the Guinness World Records, is a guy who was found to be 2.72 meters. Okay, but is this measurement precise? Well, of course not. It was simply rounded to 2 decimal places. And in fact, with a moment's thought, I think you'd realize it's physically impossible, okay, to be fully precise, not just for like quantum reasons, but also because we are just limited by the accuracy of our measurements, right? So in fact, at the present time, if we had super accurate measuring devices, heights could realistically be measured really anywhere, say up to 3 meters, although possibly there could be a giant taller than that, all the way down to 0, even though obviously you can't have someone with 0 height length, I don't know. But it'd never go there. But the point is, though, our measurements could range across a whole interval of numbers, and that's what makes this a continuous probability distribution. So the way we make sense of these is by putting this interval, or these intervals, on a horizontal axis and drawing some sort of yellow curve. Okay, that's what we call a probability density function, let's say f of x, and that's what defines this sort of variable. That's what gives this probability distribution its identity. Okay, I need to say once more, because people often get this wrong. Given any x value, say at a number a, the graph does not give you the probability of the random variable x being equal to a. It does not do this. That's because, as we've been saying, that probability of x equaling any particular value is exactly 0. Instead, we take a range of values, an interval of values, so say with b here, and we think of that whole interval, that range of values from a to b. So the probability we're looking at is the probability that our random variable x lies between a and b. Then this function f of x is defined so that the probability of x being between a and b is exactly the area under the curve between a and b. Now, hopefully you can sense that mathematically, when you want to work out the area under a curve, that just translates then to calculating the integral of f of x from a to b. Okay, and finally, one more thing to note is because we insist that the total probability is still 1 or 100%, we will insist on this probability density function f of x satisfying the property that the integral across the whole number line, which we sometimes write as the integral from negative infinity to infinity, right? That whole integral there, that whole area, the whole probability must be 1. So later you might see some real wacky constants sort of scaling these functions, and if you come across those, chances are that their job is to ensure the integral actually equals 1 and not some other random number like root 2 pi or something. But more on that later, so that's all for now, and I'll see you around.